signals will go through a reference sample. That's your control. It's a comparison. It's a calibrated thing where it's like, okay, this is what a baseline is, and your sample, excuse me, this is incorrect. I shouldn't have put the sample there. That's the beauty of this comment. Ignore that. The infrared radiation is split, goes through the sample and the reference, and they are brought back together, and they are detected. This is why I couldn't fit the word detector in the square. But the sample is compared to the reference sample, and the detector converts the radiation into an electric signal, which can be printed out on a device. Now, typically what you see, this is directly from the data book. You will have access to this. Let me see if I can make it bigger for you. Let me find that function. Okay. Now, what this shows is the location. They use something called wave number. Notice that its units are 1/over centimeters. So it's the inverse of wavelength. That's really not important for this exam. What you need to understand is the relationship between the word here and where that's located. Because these numbers indicate a fingerprint or a signature sign of a particular group over here. So, for example, common ones are these hydroxide groups, or hydroxyl groups. They are present in alcohols, phenols, which is not important what that is, but what you'll see is a definite signal in that range if there is an alcohol group present. If there is no OH group as part of alcohols or phenols, you won't see a peak in that sequence. Here's hydroxyls and carboxylic acid. Again, a definite peak there. So what you'll have to do is take a printout of one of these that would come out of the detector, and you'll see peaks in certain areas indicating the presence of one functional group, or the lack of a peak indicating that functional group is not present. Okay? Does that make sense in a qualitative sense? Okay, let's go ahead and look at some examples, because what I'm going to do is I'm going to go through these test items. Let's see if I can find an infrared printout. Here we go. So here's a problem from that section, or that would be part of that particular curriculum point. So you can see that they're just showing you certain sections of the infrared spectroscopy printout, but notice that this one shows a peak at about 3,300, wave number of about 3,300, when these are showing peaks in different locations. So with the data book present, if you look at this chart, the 3,300 is probably, 3,300 is indicating the presence of a hydroxide group, most likely in an alcohol. So if we go back to this drawing, look at the compounds to choose from. Only one of them has that hydroxide group, like an alcohol. There it is right there. So this is probably a portion of the infrared printout for this compound, because it shows a peak where the hydroxide group of alcohol should be. Does that make sense? Go ahead, Devin.
Do they give us that chart? Or do we have to
They give you what?
the chart that you just pulled up?
Yeah, that's part of the data book.
Oh, okay.
Yeah, I took this screen you see here is the data book, so it has all the pages of it. So I pulled it out just to show you. I embedded it in the. Sorry, I lost where it is. I embedded it in the video, but it is a part of the data book. Yes.
Okay.
There it is, right there. Yeah.
So the peak is the part where it's the lowest, I guess.
Yeah. Yeah, it does run downward. Let me see if I can find a better example of an infrared spec. There you go. So here's the entire thing. Now, let me give you guys some advice. This section over here is where you're going to see unique peaks. You can see one here at about 3,000. So this is the area to look for obvious peaks. This area is known as the fingerprint region. And the reason it's called that is because it's very difficult to identify a specific functional group here. However, each chemical shows a unique pattern in this area. So when you get into the higher levels of organic chem, it won't be on your test tomorrow. Oftentimes they'll talk about this fingerprint region, and there's books 12 inches thick that are nothing but infrared spectroscopy printouts. And so you can look through it, and these are pictures of this printout, and this region will match nearly specifically with your particular printout. Okay? So, if you look at this question here, it says to use Table 18 in the data booklet, that's the infrared spectroscopy printout, it says to list 4 classes of compounds that have absorptions near 1700. So if you go back to this data book and simply look, near 1700, alkenes, aldehydes, ketones, carboxylic acids. It's that simple. They'll show peaks in that region. So the reason they're choosing that is because this peak is about that point. And so that's one clue to the structure of this compound. The infrared spectrum tells you what functional groups are most likely present. And then when we combine that with the other techniques, we'll be able to get a picture of what that compound is. Does that make sense? You sure? Okay. Let's go ahead and keep going. Now, the reason I'm not going to put too much more time in this is if when I get home this evening, I'm going to actually work through some of these. I'll record myself doing so. And that is going to be the number one help for you. You're going to see me talking through how to identify what peak is what, and it's really not that difficult of a process. I guess I've covered all the things here. I'm going to go ahead and skip to the next one. Okay, mass spectroscopy. This one is probably one of the easiest ones. Let me get these out of the way. So I have a picture here of how it works and your curriculum point. Okay, mass spectroscopy. Use to determine molar mass. That's its primary use. Okay? It can give you hints as to what functional groups are there, but it's not very good at that. And here's how it works. Take a sample of your compound, and you blast it with ionized particles. Basically, you are breaking it into pieces. I know that sounds kind of funky, but you are doing two things. You blast it with these ionized particles. That's in this area. This is where it occurs. And it does basically two things. Number one, it strips off electrons. And number two, it blasts it into pieces. You may be asking, why in the world would you want to do that? Well, let's talk about the rest of this thing. Once we strip off an electron, we make it positively charged. So once it has a charge, it will be able to, it will be influenced by a magnetic field. So you can see part of this device has a magnet. So stripping off the electrons, very important. I don't think you need to know this, but I'm going to say it. The machine is calibrated so that only particles with a +1 charge pass through. If they have +2, +3, they are excluded from the process. It's not important how it works, but they strip off one electron only. Now, the reason that's important is because this device is going to measure mass. And so if we strip off too many electrons, you can get slight fluctuations, even though electrons are insignificant relative to the mass of most particles. Still, we want to retain a little bit of accuracy, so it only allows +1 fragments to go through. Second, when it blasted into pieces, it's giving you a picture of some of the parts of the compound that are present. Now, after those ions are created, they are accelerated by the magnet, and this magnet is calibrated, it turns them. It doesn't accelerate them in a straight line. They move through here, and this magnet turns them through this path. And if you know anything about momentum, like cars going around a corner at a racetrack, if the car is going very slowly, it can make turn the corner very easily. But if you're going too fast, you'll just continue and probably smash into the wall. Now, if we change the analogy from speed to size, because they're all going the same speed around this corner. So if you were going around a corner at, say, 35 miles per hour in a small sports car, no problem. You would turn that corner very tightly. If you were going around that same corner in an 18-wheeler diesel truck that's loaded up at 35 miles an hour, if it makes the turn, it's going to take it very widely. Do you understand? It's the same principle here. It's the same exact principle here. Those particles or fragments which are smaller are bent more sharply. And those that are heavier are bent less sharply. And at the detector, it's calibrated to determine the magnitude of the bend and how that relates to mass. So, in other words, imagine this was the detector, and it's calibrated so that this mark, I'm making these numbers up, but let's say that it's calibrated that things that have a mass of 50, a molar mass of 50 AMU, strike here. If they, and the source is over here, so think of the curve this way. If they strike here, or here, or here, it's calibrated to say, okay, this one's 49, this one is 48, and so on. And higher than that would be masses, or excuse me, further this way would be masses greater than 50. Does that make sense? Okay. So, one thing you need to understand. The largest sized fragment produced by this process is the original compound minus one electron. So the largest fragment, or largest peak, I say fragment, but you'll see it as like a line. The largest line is the molar mass, because it's the compound minus one electron. Just the same compound mass-wise. Okay? Some common fragments. Make flashcards tonight of these. When you see results, and I'm sorry they're too small, this one says 15. A mass of 15 indicates the loss of, that says CH3. Now think about this. If you put a compound into the spectrophotometer, if you put ethane into this mass spec, you're going to see a peak at a molar mass of, since these are both, we'll say 12, it's 24, plus 6, its molar mass is approximately 30. You're going to see a peak at approximately 30 AMUs. But in the process of blasting this in the fragments, it's possible to break those two in two. So you're going to see a peak at 15 also, because each of those two halves is a CH3. It has a mass of about 15. Do you understand how that works? And so these mass values you see here, which are in the Chem Guide, refer to it there where you can see it a little more clearly, those are indicative of certain groupings that they're going to test you on. Now we're going to do a sample question or two in a second to point that out, but please make sure you understand. Memorize these tonight, please. Okay? 17 is hydroxyl group. 29 is an ethyl group or an aldehyde. I'm copying these, so if you wait till you get home, you can see them there. This is this group. I don't even know what it's called. Without the H. It's like methanol without the H, and this is a carboxylic acid group. I know it's sloppy. You'll have a copy of the Chem Guide to see. Okay? So let's go ahead and look at an example of this. I'm going to go back to this particular worksheet, and I'm just going to scroll through until we find something that's going to work. Let me go up. Okay, we're going to have to continue this way. Here we go. Okay. That's probably more than I want. Well, we can try that. Why not? We'll see how this works out. So let me go back to the Starboard software. Let me go out. Let me capture a picture of this particular thing. That way I can write on. Okay. So here you have this compound, and we've put it in our mass spec. Okay. Now this compound itself has 48, and 9 is 57. That is 16 for 73. So its molar mass